If you rotate a ball around one axis, then another, it's not the same as doing the two rotations in the reverse order. Today, in Qiskit in the Classroom, we'll see what this ball has to do with quantum computers and one of the most famous principles of quantum mechanics, the uncertainty principle. Welcome to Qiskit in the Classroom, a video series where we break down a fundamental concept that you might encounter in a quantum computing related course. Each video is accompanied by an interactive module linked in the description below, so be sure to check that out. Today we're talking about the Heisenberg uncertainty principle. If you've heard about it before, you may have also heard the old joke about Heisenberg. One day he was pulled over while driving and the cop asked him, "Do you know how fast you were going?" Heisenberg responded, "No, but I know exactly where I am." This is kind of Heisenberg's uncertainty principle in a nutshell. You can't simultaneously know about a particle's position and momentum with perfect precision. It's often written like this. Delta x times delta p is greater than or equal to h bar over 2, where delta x and delta p are the uncertainties in the position and momentum, and h bar is a tiny fundamental constant in quantum mechanics. Heisenberg came up with this inequality back in 1927 when he was imagining how to measure the position of an electron. If you bounced a photon off of it to see where it is, that photon would inevitably kick the electron and disturb its momentum. This isn't just a statement about measurements disturbing a system. It tells us that there are fundamental limits to how much we can learn about nature. This is one example of a broader principle called complementarity, which says that certain aspects of nature are incompatible with one another and can't be observed simultaneously. For example, quantum objects sometimes behave like they're particles and sometimes like they're waves, but you can't observe both behaviors simultaneously. Heisenberg's position and momentum relation covered just one of many sets of complementary features. This inherent uncertainty has to do with how we view properties like position and momentum in quantum mechanics. Instead of thinking of x and p as variables or intrinsic properties that each particle possesses, in quantum mechanics, position and momentum are operators. They're not properties of a system, but things you can do to a system. Learning about a particle's position now requires you to perform an operation on that system and make a measurement. This operation could affect the outcome of other subsequent operations. As an analogy, think about a piece of dry wood. It has many properties, like its position, size, shape. It also has the property of being burnable and being floatable in water. If this wood were a quantum object, these wouldn't be properties that you could just know a priori. Instead, we say they're observables, things you can learn about the system if you perform some operation on it. So you would need to apply burnability or floatability operators, which would require actually trying to burn the wood or putting it in water to see if it floats. Now, the outcome of each of these operators depends on the order you apply them. If you first test burnability, the wood will burn to ash and you won't be able to test to see if it floats. But if you test floatability first, then it'll be too wet to burn. We say that the burnability and floatability operators don't commute. The order of operations matters. This leads to a fundamental limit to how well these two observables can be known about the piece of wood, since we can't say for sure whether it's burnable or floatable without knowing the context of that measurement. Now, of course, with an actual piece of wood, you could cut it in half and test both those properties simultaneously, but you can't do anything like that with a quantum particle. This analogy to wood is just that, an analogy. Uncertainty is a uniquely quantum thing. X and p also don't commute, and this property of non-commutivity is what leads to Heisenberg's uncertainty principle. In general, any two operators that don't commute will have their own uncertainty principle. The general form of the uncertainty principle can be written like this. Delta A times delta B is greater than or equal to 1/2 times, there's A and B, where this bracket is called the commutator. And that's equal to the difference between applying first A, then B, and applying first B, then A. These angle brackets here signal that you're taking what's called the expectation value of what's inside. Basically, if you made the same measurement many, many times, the expectation value is the average value of all those measurements. Today, we're going to actually test and verify this uncertainty principle on an IBM quantum computer. We'll look at 3 different observables of a qubit, show that their operators don't commute, and then finally, we'll be able to prove that the uncertainty principle holds for these qubit observables. First, a brief aside about a helpful way to visualize the quantum state of a qubit. It can be represented by a vector pointing to some place on a sphere called the Bloch sphere. I covered this in a previous video, which is linked in the description, but I'll just give you a quick recap here too. Here's the Bloch sphere. Each vector is parameterized by 2 angles, theta and phi. The state 0 is on the north pole, and the state 1 is on the south pole. And an equal superposition of 0 and 1 is somewhere along the equator, where phi is equal to the relative phase between the 2 parts of the superposition. So this state here would be equal to 1 over root 2, 0 plus e to the I phi 1, where phi is that phase. When we measure an observable of the qubit, the result is always one of 2 options, corresponding to the 2 possible states of the qubit. For the experiment we're about to do, we'll look at 3 observables and their corresponding operators, x, y, and z. When you measure any of these observables, you get either +1 or -1, with a probability for each that depends on the angle between the qubit's vector on the Bloch sphere and the measurement axis. As you might expect, z measures along the z-axis, x along x, and y along y. Now remember, we're talking about observables because with a quantum system, we can no longer just know things about the system without measuring them. And each observable has a corresponding operation because measurements require operations. It might not be obvious, but it turns out that the operations, called operators, that correspond to each of these observables, x, y, and z, are rotations of pi around their respective axes. So x is a rotation around x, y around y, and z around z. So to see if these operators commute or not, we can check to see if rotations on a sphere commute. If they do, the uncertainty principle won't apply, and we would be able to know x, y, and z about a qubit with perfect precision. If they don't commute, then we'll be able to find a new uncertainty relation for the qubit. Watch the point on this ball as I rotate first around x and then around y. It ends up here. Now let's try it in the reverse order. So I rotate first around y and then around x. It ends up over here. So they definitely don't commute. That means we can't simultaneously know a qubit's exact x, y, and z values. We'll have an uncertainty relation. We'll gloss over the details here, but we end up with 3 different uncertainty relations. So we have delta x times delta y is greater than or equal to z. Delta y delta z is greater than or equal to x. And delta z delta x greater than or equal to y. So the product of any 2 of these uncertainties is always greater than or equal to the expectation value of the 3rd observable. Let's use Qiskit to see what happens when we try to measure both z and x of the state 0. Measuring z is easy. It's the so-called standard basis of the quantum computer. Measurements are always along z by default. But to measure x, we need to perform something called a basis change, basically rotating the Bloch sphere so that x is now pointing up where z used to point. To do this, we use a Hadamard gate. So the full quantum circuit will look like this. We measure in z, apply the Hadamard, and then measure in x. If we use the Qiskit primitive sampler to run this experiment many times, we end up with a histogram of measurement outcomes that looks like this for the z measurement, and like this for the measurement in x. So as you can see, we measured the qubit to be in the 0 state along z with pretty close to 100% certainty. But along x, we knew basically nothing about the qubit state. It was measured to be either 0 or 1 with equal probability, meaning our uncertainty in x was about as big as it can be. That gives us a little sense for this trade-off of uncertainties, but we can do a bit better. On our quantum computer, we can use a Qiskit primitive called estimator to find the expectation values of our observables x, y, and z, and the uncertainty in each. Let's try it for the state pointing in the plus x direction on the Bloch sphere. We'll use estimator to calculate the uncertainties in x and z for this state and the expectation value of y. With this state, we get this result from Qiskit. When we take the product of the two uncertainties in x and y, we see that, as expected, it's larger than the absolute value of the expectation value of y. But this was just for one particular state. We want to make sure this inequality holds true for all qubit states. So let's use estimator again, but this time we'll ask it to scan through the values of a parameter and to find the expectation values at every single parameter value we give it. Here, the parameter we want to scan is the angle theta on the Bloch sphere, so that we check the inequality for all the qubit states that lie on this arc that intersects the xz plane. When we do this, we get a plot as a function of the angle theta. The red curve is the product of the two uncertainties, and the orange curve is the expectation value of y. As expected, the product of the uncertainties in x and z are much higher than the expectation value of y. But that wasn't too hard to satisfy the inequality, because the expectation value of y was so low. It was 0 for all the states on this arc. Let's do a similar scan through the theta values, but instead of scanning in the xz plane, we'll set phi equal to pi over 4. So we're looking at the qubit states that lie on a different arc on the sphere. Here we see the inequality is tested a bit more, since the orange curve and the red curve are closer together, but the red is always above the orange and the uncertainty principle still holds. We haven't checked all the states yet, but hopefully you're starting to get the idea. There's a fundamental unknowability about any two complementary aspects of a quantum system, including this qubit we've been using. The uncertainty principle forces us to confront the fact that no matter how hard we try, no matter how clever our measurements are, we will never know everything with perfect precision. There's no getting around it. Really, if you don't believe me, or even if you do, I challenge you. Go check out the module linked in the description and try to beat the uncertainty principle. Thanks for watching, and I'll see you next time.